let's pursue the idea of circular orbits. Later in the course we will cover elliptical orbits, but now let's exclusively talk about circular orbits. Now this is the mass of the Earth, and in a circular orbit is an object with mass m, a satellite, and m is way, way, way smaller than the mass of the Earth, and the radius of the orbit is r, and this object has a certain velocity v, tangential speed. The speed doesn't change, but the direction changes, and there has to be a gravitational force to hold it in orbit, and the gravitational force is exactly the same as the centripetal force. We've discussed that many times before. And so the gravitational force, which is necessary to make it go around, I could also say the centripetal force is necessary to make it go around in a circle. That gravitational force equals m Earth g divided by r squared. This is now the distance from the Earth to the satellite, and that must be equal to m v squared divided by r. And that is that tangential speed that you see here, which a little later in time, of course, would be here. I lose my m, and so you see now that the orbital speed, not to be mistaken for escape velocity, the orbital speed is exactly the same what we have there, except the square root of 2 divided by r. This is now r, and there was r Earth. If you know r, then you can calculate the speed in orbit. If you know the speed in orbit, you can calculate r. And so the period of going around in the orbit t equals 2 pi r divided by the orbital speed. And when you do that, you get 2 pi, you get an r to the power 3/2, and you have downstairs the square root of g m Earth. Let me move this in a little. 2 pi r to the power 3/2. So again, if you know the radius, if you know how far you are away from the Earth, the period follows uniquely. If you know the period, then the distance to the satellite follows uniquely.